Right, page 296, exercise 13. A carpenter and his helper can do a job in 4 hours. Working alone, the carpenter can do it in 6. Some help. How long would it take the helper to do the job alone? So this is one of these rate of accomplishment things where you just have to think in the following terms. The carpenter can do the job together with the other employee in 4 hours. In other words, 1/4 of the job per hour. Working alone, the carpenter can do 1/6 of the job per hour. So how much does the helper help? Well, here's how the equation gets laid out. Together, they do 1/4 of the job. 1/4 job in each hour. And that would be the sum total of the carpenter's rate of accomplishment and the helper's. Now the carpenter can do 1/6 of the job by himself or herself per hour. And we will add to that the helper's rate of accomplishment, which is 1/x. We don't know how much the helper gets done in an hour, 1/4 of the job. So even if we look at that algebraically, we can simply eliminate the word job from all of these, and we get an equation that looks like this. 1/4 equals 1/6 plus 1/x. And we need to solve for x. And that's going to turn out to be a quadratic, but it won't be too difficult. Let's look at exercise number 14, and this once again is something similar that we've seen before. The rate of a stream is 4 kilometers an hour. Scott paddles downstream a distance of 9k and then back upstream to where he started. Sounds like a really good day. If the total trip took 10 hours, what is Scott's rate of paddling in still water? Well, if anybody paddled for 10 hours, I imagine that they would have slowed down throughout the day, but we won't worry about such realistic details. The total trip took 10 hours. What's his rate of paddling in still water? Let's look at the various equations that we have for distance and time. Distance equals rate times time. And rate equals distance over time. And time equals distance over rate. And in order to solve this, our first step is to decide which of the 3 equations to use. In this equation, I'll tell you that it tells us the total time. It tells us 10 hours. It doesn't tell us a rate, and it does tell us a distance, and we might be able to work with that, but I'm going to choose not to because the distance is broken up into 2 different rates. So it's a whole lot easier to start with this one here because we do have a defined time. So the time was 10 hours. And in that time, he went in 2 directions. So there's the time he went downstream, the time he went upstream. There's the distance he went downstream and upstream as well. Okay, so we don't really care how much time he spent in each of those, but we do know the distances. So time equals distance over rate. So distance in one direction over the rate in that direction, plus the distance in the other direction and the rate of that direction. So when he went downstream, he went 9 kilometers, and he went there, and remember we're just filling this in here, distance was 9 kilometers. So downstream he went 9 kilometers, and his rate there was his still water rate plus 4 because he was going downstream and the stream was carrying him. Then he turned around and he came right back another 9 kilometers. That's his distance back upstream. But his rate back upstream was going to be slower. It's going to be against the current, so 4 kilometers slower than his still water rate. So there's our equation, and that simply has to be solved for r.